Dear student, let us begin lectures on machine design part 1. This is lecture number 19 and the topic is design of power screws. Now, in lecture number 18 you are taught the kinematic and the static analysis of a power screw. In this lecture you will learn how to design such a power screw. In order to elucidate the design principles, we take a simple example in an example of a C clamp. Now, here let me draw a C clamp first. This is a C clamp, this is the screw and this is the clamp. Now, it is held fixed to the ground, that is it is held by some device, and the purpose of the C clamp is to give a pressure, a compressive force there on this surface. Now, we have to look into details of these portions of the C clamp. Now, you see, whenever we want to give a pressure, we have to turn this screw and the whole body turns, but we do not want this surface to turn so abruptly. So, therefore, we need to stop this turning motions when it gets transferred to here, and this is done by means of what is known as a collar or thread collar. So, this is kind of thread thrust bearing which we use here, and the detailed picture will be, if you consider this to be the clamp, there is a little hole over there in which a fastener is connected. So, therefore, when it rotates, then it rubs along the surface, and because of the frictions we need to overcome these frictions, and this is done by applying the torque. So, the torque is required in order to overcome the friction over this area as well as the friction here. Now, whenever we want to design, then we have to concentrate on 3 portions, as it is very much clear that these portions, which let us say we call L1 the length, this is the nut, the length of the nut let us say L2, and this part which we designate L3. Now, there will be several kinds of stresses. First of all, if we designate x from this distance, then there will be the compressive stress. The compressive stress distribution is somewhat like this, is the Nx, that is the normal force, and here are these things, that is L1, this distance L1, L2 and L3. Now, here there will be pure compressive stress and the magnitude is, so this is negative, the magnitude is the P, the point of the load over here, and then it gradually goes to 0, and here this part is not under any compressions. So, therefore, the normal force distribution will be something like this, and this is purely negative. Now, with the normal stress, that is the normal force, there will be the normal stress, and the normal stress is given by this formula which is very well known, that is Nx divided by A times, or this is the area of the threaded section. So, this is the critical sections of the screw, and that will be the root of the thread. Now, this is the normal stress and this is compressive. So, this is negative stress. Then of course, we have the torque. Let me draw the torque distribution. Now, here up to this point there will be only the torque which is to overcome the collar friction here, that is, as we have mentioned before, there will be friction. So, we want to overcome these frictions, and that remains constant here. Then we have to add the torque, that is the torsion due to the friction in the thread, and that varies almost linearly, and beyond this lane, that is L1, is subjected to both the addition of these two, that is T c, the collar torque, and T s, this part. So, therefore, this will be T c plus T s, this length. So, this is the torque distribution, and we know that whenever there is a torque, we have the shear stress. This is equal to 16 times the torque divided by pi d c cube. So, this is the shear stress and this is the normal stress. Sometimes, of course, depending upon the application of the load of this this torque, we may have bending stress. For example, let us consider not a direct application of the torque, but with a handle we apply some force over here. So, if we consider the handle to be a rigid body, then the equivalent force system will be a torque just like this, and in addition there will be one force. So, this force causes bending, and this bending stress will be very high over here. Of course, we do not consider any bending stress beyond this, because we consider this to be clamped. So, therefore, the bending stress will be something like this, and this is the bending moment distribution, and the bending stress, all we know, this is again normal stress, and this will be 32 m by pi d dc cube. So, there are different kinds of stress available here. Now, you have to find out, you have to use the failure criteria and get the correct value of dc, that is the root diameter of the thread. Now, there are few failure criteria which you have say we have tau max, this is the failure by maximum shear stress, and this will be equal to sigma. Now, we will have to consider the overall sigma. So, that is depending upon the sections. Here you have the bending stress, here you have the compressive stress, and of course, torsional stress will be present always. So, the sigma tau max will be sigma by 2 square plus tau square, and that must be less than equal to tau allowable. Now, this is the criteria with the maximum shear stress. In some materials, of course, in most of the materials, the better criteria is the von Mises stress, which is given this way. This is von Mises equivalent stress, and this is given by sigma square plus thrice tau square, and this must be less than equal to sigma allowable. So, you know all this. Now, using this failure criteria, you will have to find out the value of dc. Then, once the diameter is selected, we have to consider one more thing. That is, although it does not belong to the theory of failure, but there is one instability problem for which the material may fail, and that is known as buckling. So, the buckling is one of the important criteria which has to be considered here, because this part is subjected to the compressive stress. Once a material is subjected to the compressive stress, then all of a sudden the material may become unstable, the whole structure may become unstable, and it may actually bend like this, and whenever it bends, then a large amount of bending stress is developed over here, which ultimately leads to failure. So, we will have to check for the buckling. Now, all of you know that the critical load for buckling, the very simplified analysis of buckling critical load is given by Euler formula, and that is equal to C times, which is C is a constant, I shall come to that later, C times pi square E I divided by L square A, which you can write C times pi square E by L by K square. Now, this is the critical load for Euler's equations, but where C will be a constant, and that depends upon the boundary conditions. Depending upon the boundary conditions, the failure may start at different region. Now, here one reasonable guess of boundary condition will be, let us assume that this part is clamped, that is, here we are considering a buckling of a beam which is fixed at one end and free at other end and subjected to a pressure P. Then of course, the value of C will be in that case 0.25, and then we have the Euler critical load for buckling. But if L is very small compared to the K, now I did not mention, then K is the radius of gyrations, and this is nothing but I by A. So, this is the radius of gyrations, and we have this formula C pi square E by L by K. Now, whenever this L is very small compared to K, then we can see that F E could be very high, but in fact it does not happen, because before it reaches very high level, then the material will be crashed. So, it will be smashed, and we do not allow that. So, therefore, we need some correction whenever this factor is very small, and the one of such correction formula was given by Professor B. R. Johnson, and this is known as Johnson's formula. Now, if you consider this if you remember this formula, then the Johnson's formula will be given by this one, where F Johnson divided by A will be equal to the yield strength minus 1/4 yield strength square. So, this is a parabolic formula, and this is divided by F E by A. So, now this is a parabolic formula given by Johnson, and we have to use this formula in order to check whether the given load, that is, once we have decided for the diameter, the core diameter, then we have to decide whether the given load is more or less than F j. Definitely, if the load is more than F j, then we will have to increase the diameter by some amount, and that then again we have to check this formula. Now, this is about the buckling. Now, we have known sigma, we have known tau, and we have calculated the diameter, but in order to calculate the shear stress, we must know the collar frictions. Let us talk a little bit about this collar friction. Now, the collar frictions, if you look little bit closely here, this thing, then there is a collar and this is the recess. Let us say the outer radius and the inner radius, this one is R2 and the inner radius is R1 say. So, this is R1, and then whenever we start from a smooth surface of a new surface, then definitely the first reasonable assumption will be that the pressure distribution is uniform. So, this is subjected to pressure and this is uniformly distributed. Therefore, we have P, which is a constant. How to get the value of this constant? This comes definitely from P equal to then the total force divided by the area, that is pi r2 square minus r1 square. And then how to calculate the torque from it? We know, given a small area dA, then the frictional force will be mu times the pressure on it. So, the net force, that normal force on this elemental area dA will be P and dA. Now, this is again the normal force is P times dA. So, therefore, the friction force will be mu times P times dA, and then we have to find out the torque. Now, the direction is always opposing the motion. So, the direction will be always tangential here. Therefore, in order to calculate the torque, net torque, then we will have to multiply it by r, the radius of this elemental area from the center, and then we have to integrate over the entire A here, and this will be the torque. Now, if you calculate, then the torque becomes then this torque collar becomes 2/3 pi, then we have P r2 cube minus r1 cube divided by r2 square minus r1 square. So, this is the torque required to overcome the collar frictions. Now, once it has started working, then after sufficient wear and tear, then the surface becomes smooth, and then the pressure does not remain anymore uniform, and what the reasonable assumption will be that wear is uniform. Then after some time is evolved, then we assume that wear is uniform, and definitely wear remains, wear depends on both the normal pressure as well as the travel distance. Again, the travel distance is proportional to the r, the radius from the center. So, therefore, the wear constant implies P times r is constant. And again, if you do the same calculations, what you get is this form, that is for constant wear we have this is mu by mu times P by 2 times R1 plus R2. Now, let me make a small correction here. I wrote pi, but this should be mu, as you can very well see, because it depends on the coefficient of frictions. So, therefore, T c prime, that is the torque required in order to overcome the collar friction under the condition of uniform wear, is given by this form. Then it is very easy to check that if R2 is very small, then what happens? Then T c, if R2 is very small, that is goes to 0, then T c prime is about 3/4 times of T c. So, therefore, once it has worn out sufficiently, then the friction becomes, or the frictional torque becomes quite low, at least the low compared to the first case when the pressure was uniform. So, this is how we could estimate the shear, the torsions here in the collar. Then of course, the torsion in the screw, that is the torque in the screw, that is torque to overcome the friction in the thread, will be given by the known formula which I derived in last lecture, and that was equal to P times mean radius of the thread and times tangent of phi plus lambda, where phi is the angle, helix angle, and this is nothing but lead divided by pi pitch diameter, and tan lambda is nothing but mu at thread. So, this is the friction coefficient between the screw and the nut, and the friction force appears in the thread. So, we now know the individual values of T c and T s, and from this we can calculate the shear stress due to torsion. Now, let us come to the region which is very very important, namely the region of engagement between the screw and the nut. Now, see, let me draw the part of the thread over here. Now, this is a part of the thread and it is subjected to the pressure P and the frictional force over here. And if you remember last lecture, then the normal force, that is the normal force on it was P divided by cosine phi minus mu times sin phi, where again phi is the helix angle. Now, for a normal thread, phi is very very small. Therefore, this term is very small and it is again multiplied by mu, which is again a small number. So, therefore, the contribution of this term is very very small, and if phi is very small, then cosine phi is almost equal to 1. So, therefore, this is very much equal to P. Now, this amount of normal force is distributed or acting uniformly over the thread. So, it develops what is known as the bearing pressure on the thread. Let us look at the bearing pressure now. Now, as I said, the pressure is uniformly distributed over the thread. So, if you consider a single thread, then the total force on the single thread will be equal to P by N, where N is the number of threads in engagement with the nut, and it depends upon the pitch, that is N will be equal to 1 upon pitch, that is equal to number of thread per unit length, and times the height of the nut, that is this length. So, this is the total number of threads in engagement. Hence, the total force per thread will be here this divided by the area, and what will be the area? Area will be definitely pi times d mean and times this length, which is the h, which is equal to the height of the thread, and that is equal to P b, that is the bearing pressure. Now, this bearing pressure must be low as low as possible, because depending upon the pressure the wear and tear will take place, and this is detrimental to the life of screw, and the screw may get damaged. So, therefore, P b is one thing which we have to control, and that could be done by selecting the h. Again, h is for a square thread, h is nothing but P by 2, and hence we have to check for this P b such that this P b becomes less than some bearing, allowable bearing pressure. There are other kinds of stress in the thread. So, if you consider a little part which is, let us say, unit distance apart and look from this side, then what you see, it looks like a cantilever beam, because this side is firmly grounded. So, therefore, this is cantilever beam whose height length is h and this length is b, and it is subjected to uniform pressure, again P, which is equal to F by N. So, therefore, for this kind of force we shall have both the shear stress here and the bending stress. What will be the value of the shear stress? The value of the shear stress here the shear stress V at x equal to 0 is nothing but P times H. Hence, this is the shear force, therefore, the average shear stress will be P times H divided by the area, and area was unity, the width, and the height, that is B. And for again for square thread, H is equal to B is equal to P by 2, where P is the pitch of the thread. Now, we can even go further, because this has a uniform cross sections, then the shear stress distribution is not uniform. In fact, the shear stress is distributed parabolically, and this is the roughly the distribution of shear stress. The maximum shear stress occurs somewhere here, and the value tau max will be 3 by 2 tau average, that is the maximum value is 1.5 times the tau average. So, this is about the shear stress, it is maximum here, minimum here, and varies parabolically. What other stresses? The other stress is the bending stress. It is easy to calculate the bending stress. First comes bending moment, which is equal to P h square by 2. Therefore, the bending stress is m, and here the maximum bending stress will be at B by 2 divided by I, which is equal to 12 times 1 times B cube. So, this is the formula for getting the bending stress. Now, we know how to calculate the shear stress and bending stress in the thread. Then different section of the thread will undergo different state of stress. Let me point out now one. If you consider the cross section of the thread, then this point will have the compressive stress. Suppose it is here, then the compressive stress is P, there will be compressive stress. So, if you have one element at point A, if you draw the state of stress, there will be compressive stress, okay, with sigma z say. There will be the bending stress, which is sigma b, and the value which I have already calculated just now. Then there will be the shear stress, and shear stress not from the thread pressure, but from the external torque, and that is appearing here. We have countering shear stress, and this is the state of stress at this point. Similarly, if you want to draw the state of stress, you can do it quite quickly. Now, once the state of stress is known, then you can use those formula, that is either the maximum shear stress formula or the von Mises theory of failure criteria, and find out the safe limit, that is whether the thread will fail or not. Now, there is one problem in this very simple design, that is, here we have assumed that all the threads are having uniform pressure, that is, the engagement, if there are n number of threads, then all the threads will take the same load, but this is not so, and the problem of getting the stress this force distribution per tooth will be very complicated, and it is in fact statical indeterminate problem. In order to calculate the stress distribution here, we have to solve a different, well, a complicated elastic problem. Usually what is seen from experiment, that the first few threads will take up the majority of the load. For example, it was found out that the first thread which is engaged in the knot. So, this, if this side is the portion of the knot which is directly first in contact with this thread, then this thread will take up about 38%, and usually as you go along, then of course the percentage of load carried by individual thread will be very, very small, and beyond 7th thread the threads do not carry any load practically at all. So, therefore, if we think that by increasing this height of this knot we can have the low bearing pressure or low shear stress in the thread, this is wrong assumptions, because all the threads are not under uniform pressure. So, one way of having a good design is that assuming n equal to 1, that is the number of thread in engagement is 1, and the load, instead of taking the full load, let it take 0.38 of the load, and then we calculate for the stresses and find out whether this is in safe or not, and this is very conservative design. So, this was roughly the design procedure of a C clamp. Now, let us make a summary. What are the stresses in power screw? Power screw will have different kinds of stresses. One is axial compressive or tensile stress. Now, depending upon the situations, the part of the screw may have compressive stress or part of the screw may have tensile stress. So, you will have to calculate for the for both the cases. Now, whenever the screw is under compressions, then in addition to checking the crushing failure, we will have to check the buckling failure, because this is very dangerous. Buckling occurs all of a sudden, and suddenly you will see the material or the structure gets deformed, and a large bending stress develops and it fails. So, therefore, this is a very dangerous thing and has to be prevented, this buckling. Then comes the shear stress due to torsion. Here we have two sources of shear stress, that is, one is the torsion required to overcome the friction resistance, and that occurs only in the thread and thread between nut and the screw. There is another source of the external torque which is equal to the frictional resistance at the collar or in the bearing. Then comes the bending stress. Again, the bending stress does not happen always. It happens only in those cases and depending upon which depends on the applications. Then comes the bearing stress on threads. So, this is very important. Most of the power screws fail by this bearing stress, and bearing stress, if it becomes very large, then lots of wear and tear goes on, and that has to be prevented. So, this bearing stress is very important and has to be taken care of. Then the shear stress in threads due to pressure. You have seen that the shear stress developed in the threads, that is because of the pressure. Then the bending stress in threads due to pressures. Now, all of the stresses due to these last three criteria must be taken care of, and we will have to find out the equivalent stress, that is the maybe when you use the von Mises criteria you will have to find out equivalent normal stress, or if you want to use maximum shear stress then you will have to calculate the maximum shear stress. Everything depends upon the state of stress at different points. Now, let us come to the materials which are used for screws and nuts. The screw materials may be steel without hardening, that is we may use sometimes soft steel, then steel with hardening. And what is the purpose of that hardening? Now, we know the lots of wear and tear will take place between the screw and the nut. So, in order to have the wear minimum, we will have to make the surface of the thread wear resistance, and that could be done by hardening. There are various methods of hardening, but all of them introduce some sort of deformations. We have to take care that sufficient wear resistance is developed, as well as the deformation due to hardening is minimum, because that will lead to inaccuracy in the thread profile. One such method of hardening which proves to be very effective is nitriding, and here you will see that the wear resistance gets improved, as well as the work hardening becomes very small. There are other methods using electromechanical hardening. The nut materials, they are usually of softer material. Sometimes we take brass or bronze. Cast iron is also taken. Now, cast irons are used as nut material, as it is whenever the load is small, as well as the speed, that is the velocity, rubbing velocity is small. If we want to increase the load, then we have to we use the cast iron, but the surfaces are babited by some alloying elements. So, these are roughly the materials used for screws and the nuts. Now, let us come to the bearing pressure of different kinds of threads. That depends again on the application to applications. In the hand press, you will see the materials are normally the screw material is steel and the nut material is bronze. The pressure is 17.5 to 24.5 megapascal, which is very large, but the rubbing speed here is quite low. And whenever we have such large bearing pressure, this is the safe pressure for bearing, and whenever the bearing load is very high, then that has to be lubricated properly, otherwise it will wear out. Then we have the screw jack. The screw jack can be made of steel. The screw is steel, nut is cast iron. Here 12.6 to 17.5, little lower than that the before. The speed is of course less than 2.4 meter per minute. So, this is quite small speed. We have another steel. When we use the bronze, then of course the bearing pressure is almost the same, to 11.2 to 17.5, but with bronze we can go up to 3 meter per minute rubbing speed. For the hoisting screw material is steel and the nut is cast iron. Here the bearing pressure is quite small, 4.2 and 7.0, whereas the rubbing speed here is quite high, 6 to 12 meter per minute. It is again very moderate speed, not very high, not very low. We may have bronze. Now, with the bronze, of course, the bearing pressure could be little higher, 5.6 to 9.8 megapascal. When we have lead screw, now lead screw are used for giving feed motions, and that has to work very fast. So, therefore, the rubbing speed is very large, but now the pressure becomes quite small. That is, when we use the screw material as steel and the nut material as bronze, then the rubbing pressure becomes, or that is bearing pressure becomes 1.05 to 1.7 megapascal. Then one more thing in order to design is the coefficient of friction for thrust collar. Again it depends, again the coefficient of friction depends upon the material of contact, that is whether the steel or cast iron or hardened steel on cast iron, hardened steel on bronze, etc. You will see the starting coefficient of frictions, that is the static coefficient of friction sometimes called, it is quite higher than that of the running, that is the kinetic coefficient of frictions, that is very much known to you. Now, soft steel on cast iron has a starting coefficient of friction 0.17 and the running coefficient of friction is 0.12. When you use hardened steel, that is after hardening and again cast iron, then the starting coefficient of friction is 0.15 and the running coefficient of friction is 0.09. Then the hardened steel on bronze, now use the bronze which is a softer material, then of course the friction becomes very small. You see the when you use the hardened steel and bronze, it becomes 0.08 in starting conditions, that is the static coefficient of frictions, and the kinetic coefficient of friction is 0.06. Soft steel on bronze, the starting coefficient of friction is 0.10 and the running coefficient of friction is 0.08. Again these are representative values, you should not take it very rigidly. So, it is usual practice to take such values, but one can differ depending upon the situation to situations, and also the coefficient of friction depends on the environmental conditions also, that one must not forget. So, let us see what we have learned today in this lecture. We have designed, we have taken a very small example, a simple example of a C clamp. The design is to calculate the diameter of the thread of the screw. Now, that is based on different forces, the compressive stress as well as the torsion. The compressive stress, again compressive and tensile stress may appear, and the torsion which we have to take into account. Then comes the thread. The thread is very important, and we have to consider the bearing pressures in thread as well as the shear stress in the thread as well as bending stress in the thread, and depending upon everything. So, combining all, we will have to find out the safe diameter that is used for the screw. Now, let us come to the homework problem which was given in lecture 18. The problem was, the position of an automobile jack shown is controlled by screw ABC, single threaded at each end. The screw has nominal diameter 20 millimeter. The nominal diameter is 20 millimeter. It was Acme thread. Now, we know that Acme thread has profile this thread angle is 29 degree. Both screw and nut are made of steel. Determine the magnitude of the couple to raise the load. Let us see, the important thing is that it has Acme thread, then the material screw and nut. Now, remember I gave you one table, let me reproduce the table. Here is the table which I showed in the last lecture. The coefficient of friction for thread, the screw material and nut material. Let us assume that steel is steel dry and the nut is steel. So, therefore, we have to take the coefficient of frictions from this data. We choose the minimum coefficient of frictions, that is mu is 0.15 and calculate. So, this gives the minimum torque required. Here comes the solutions. When you look up the table, that is given in any design handbook, you see that for 20 millimeter nominal diameter, the chord diameter is 15.5 millimeter and the pitch diameter is, or pitch is 4 millimeter and the thread angle is 29 degree. So, therefore, we know the phi, that is tangent phi will be equal to pitch, it is single threaded, tangent phi is 4 divided by pi, and we will have to consider the pitch diameter, and the pitch diameter is nothing but the, here for the acme thread, pitch diameter will be equal to the nominal diameter plus the chord diameter by 2. So, this is nothing but the mean diameter. So, when you calculate, you get the value of phi. Then you have to calculate the value of lambda, that is tan lambda is equal to 0.15. Then from this given data, we will have to calculate the force on the knot. So, that is again done by elementary static analysis. If you consider 4 kilonewton here, then of course, you get this was 25 degree and again this is 25 degree. So, we have to calculate the force over here, then this force is again transferred to this knot again from this side, and we have to calculate the net force. So, the net force will be here, net force on each knot will be equal to external force divided by tangent of -25 degree. So, this is the force which we have to which the thread has to withstand, and when we have one thread, one bolt, then the torque is given by F times d, again dn plus dc by 2, that is the d mean by 2, and tangent of phi plus lambda dash. Now, for the acme thread, you know lambda dash, tan lambda dash is nothing but mu divided by cosine of theta by 2, that is 29 degree by 2, and when you calculate that, you get the value of the torque, but there are two threads which are opposite handed, and therefore, the total torque will be equal to double of that. So, hence the answer is here, and when you calculate everything, what you get, the torque required will be equal to about 26.4 Newton meter. So, this is how we have to solve this kind of problem. So, let us now once again recapitulate. In last two lectures, we have learned the kinematics and statics of a thread of a power screw, and then today's lecture we have known how to design such a power screw. The most often used screws are with acme thread or square thread. They have their respective advantages and disadvantages. The screw materials are mostly steel, hardened or soft. The nut materials could be bronze, brass or cast iron. So, you know now after this lecture, you know how to calculate, how to design a safe power screw. So, thank you. Dear student, we are now going to begin lectures on machine design part 1. This is lecture number 20 and the topic is shaft coupling. So, this is the first of the lectures on the same topic. Now, couplings are normally used to connect two shafts axially. Now, the shafts are usually manufactured in small pieces in order to avoid the difficulties or disadvantages of transport problem. And whenever they are connected by means of these couplings. Now, there are another device, there is another device which serves the same purpose. This is known as the clutch. The important difference between the clutch and the coupling is that the clutches are used in order to disengage and engage the shafts frequently, whereas the couplings are used to fasten them together, and this is permanent connections and they are only opened up during replacement or repair or maintenance. So, this is one of the important difference of coupling. Now, the couplings are used mainly to transmit power without any loss. The transmit, this is now this is what we want to say, that transmit power without any loss, that is very much expected. And second, provide for shaft misalignments. Now, shafts are normally installed without any misalignment, but because of various reasons there will be inevitable presence of misalignments. Now, the misalignments may be of different types. Let us see, suppose we want these shafts to be connected this way. So, this is the ideal situations, two shafts axially connected in this fashions and there is no misalignment. There may be misalignment, for example, one shaft is here. So, this one is ideal. There may be misalignment when one shaft is here and the other shaft, the axis of that shaft is offset by certain distance delta. This is one kind of misalignment. There may be another kind of misalignment, that is, there is one shaft, then other shaft is skewed a little bit by an angle alpha. This is one such misalignment. There may be a combination of these two, that is, a shaft may be there and the other shaft is both angularly misaligned, there is angle alpha between these two axes and there is offset delta. So, there are four kinds of misalignments and those are to be avoided, but normally this misalignment occurs in practice and it is difficult to avoid. Then we have provisions, that is, couplings are to be used in order to provide for end movements of the shaft. Now, the types of shaft coupling. There are two types, two principal types of shaft coupling. One is rigid coupling and another is flexible coupling. As the name suggests, the rigid couplings are couplings without any flexible member. There are different kinds of rigid couplings. We have to discuss four which are the principal types of rigid coupling, namely the first one is flange coupling. This is the most commonly used coupling. The second one is sleeve or muff coupling. The third one, clamp coupling, or sometimes it is called split muff coupling. Then compression coupling. Flexible couplings are of two types. One is coupling with kinematic flexibility, that is, we insert certain members which undergoes rigid body translation or rotation, but that gives a little bit resilience or flexibility in the overall joint. The second type is coupling with resilient members. Now, here we introduce some members which have the flexibility. So, this is inherently a flexible couplings. We are going to discuss in this lecture the principal types of rigid coupling. Now, let us come to few types of flange coupling. Now, flange couplings, you see, these are couplings, again rigid couplings, and the coupling is done by means of two flanges. What you see here is the cross section of such a flange coupling. Here the shaft, and on top of it this part which is known as the flange. It has two sections, one is here, which is a relatively thick part, it is known as hub, and this part which is relatively narrow, then this is known as the flange, and these two flanges are connected by means of few bolts. Parameters of flange couplings are given here. D1, as I said, which is equal to the bowl circle diameter, this is roughly taken to be twice d, small d, that is the diameter of the shaft, plus 50 in millimeter, that is 50 millimeter, or it may be 3d. Now, why all this? Because the couplings are now manufactured by different manufacturers, and so we have to come to a standard. So, these are normally the standard follows unless otherwise specified to the manufacturers. There are catalogs available from the manufacturers, and we will have to look up into those catalogs to find out exact diameter, but what you see here are normally the usual diameters or usual dimensions maintained in practice. D2, which is the hub diameter, is 1.5 times d plus 25 millimeter, or it may be twice of diameter of the shaft. Everything is mentioned in terms of the diameter of the shaft. The outer diameter is 2.5 times d plus 75 millimeter, or roughly 4d. Length, which is quite important, it is about 1.25 times d plus 18.75 millimeter. You see this odd figure, but these are standards. Tf, the width of the or the thickness of the flange, which I have told in the last slide, is 0.5 d, and n, that is the number of bolts, which that may be 3 for d up to 40 millimeter, 4 for d up to 100 millimeter, 6 for d up to 180 millimeter. So, these are the usual dimensions which are maintained in practice. Now, let us come to the design criteria of flange coupling. So, these are the two flanges which are connected by bolts.